Now we're going to move on to the more exciting stuff on designing controllers, on feedback control systems. So this is an appropriate time for us to take a step back and and look back at the path we had taken to come to this, to arrive at this point in the course. We started off with modeling processes and derived ordinary differential equations, which we then used Laplace transforms to convert those ordinary differential equations into transfer functions using simple algebraic manipulations. We've then used poles and zeros of transfer functions to relate, to describe the dynamic behavior of these transfer functions. So now we know how different types of processes behave. And that understanding is what we're going to use to design feedback controllers. In particular, in Chapter 8, we're going to look at proportional, integral, and derivative controllers. Eventually, we're going to put these three controllers together to develop a new controller called a PID controller. The PID controller incorporates the advantages of the three controllers, P, I, and D controllers. In the next lecture, we're going to look at the typical components or the basic components of a standard feedback control loop. We're going to do this using the blending tank example. And in the tutorial, you had already looked at the basic components of a feedback control loop that included a sensor. In your case, in the tutorial, the sensor is a temperature sensor. The controller is the Arduino board, and the final control element or the input to the process is the voltage coming out of the Arduino board. The process itself was the transistor. So let's first start with the basic components of a standard control loop. Here is a blending process that you had already seen in the previous chapters, in Chapter 1 in particular. The blending process has a controller on it that's used to control the concentration in the exit stream. Obviously, in any feedback control loop, we need to have the process that is being controlled, which in this case is the blending tank. In addition to that, we need a sensor-transmitter combination that is used to measure the concentration of component A in the exit stream. Often, sensors come with a transmitter attached to them because the signals coming out of a sensor are typically very weak electrical signals. And often, in a process, the sensors are located very close to the process itself, but the processing of the measurements from the sensors and the algorithms reside in a computer that is not anywhere near the process itself. These computers are most likely in a control room that is quite far from the process and the sensors. So the signals coming from the sensors have to be sent via cables to a different location for processing, which means the signals have to be strong enough so that they can be transmitted to a different location. Weak signals that are generally given out by sensors cannot be transmitted over such long distances without the signals getting corrupted or without the signals being very noisy. Therefore, we often have sensors come with a transmitter which magnifies the weak signal from the sensor and transmits across different units and or to the control room. Now this signal from the sensor is an electrical signal in the range 4 milliamps to 20 milliamps or 1 volt to 5 volts. That signal is sent to a controller. The controller resides in a distributed control system, often in the control room, DCS. The controller also receives a set point supplied externally. The output from the controller is an electrical signal, again in the range 4 milliamps to 20 milliamps or 1 volt to 5 volts. And that signal then has to be sent to a control valve. The control valves are mostly pneumatic valves, and they operate by adjusting the air pressure supplied to these valves. The signal out of the controller is sent to an IP, current to pressure transducer, which is then converted into a pneumatic signal in the range 3 to 15 psig. The pneumatic signal is then sent to the control valve to move it. So a typical control loop consists of, in addition to the process, a sensor-transmitter combination, the feedback controller itself, which resides in a computer, current to pressure transducer, final control element, the control valve, and of course various transmission lines between instruments. Recollect that a feedback control controls a control variable by adjusting a manipulated variable, or it measures the control variable and adjusts the manipulated variable. The control objective here is to maintain the control variable at a desired value at a set point that is given externally to the process. Now, I'm going to introduce you to a control algorithm called proportional control. Now, instead of directly presenting to you the equation that describes a proportional controller, I want to take you through an intuitive, crude approach of designing a controller and then lead you to the proportional controller. So let's consider a process where we're trying to heat the liquid in a tank. Let's assume that the inlet flow rate and the volume in the tank are constant, because we just want to have one control loop that is controlling the temperature. We can of course have another control loop that's controlling the volume in the tank or the flow rates. Just to keep it simple, let's assume that the volumes and the flow rates are constant, and therefore the only variable that we need to control here is the temperature. Now we can make a couple of simple observations. If the temperature in the tank is greater than the set point, the desired value, we of course need to decrease the amount of heat being added to the tank. If the temperature is less than the set point, then we need to increase the amount of heat added to the tank. Let's define what is called a control error as the difference between the set point and the temperature in the tank, T. Now clearly, this control error represents the deviation of the temperature from the set point. Now we can try to translate the two conditions 1 and 2 here into conditions on the control error as follows. If E of t is less than 0, it means the set point is less than the temperature, and therefore we have to decrease Q. And if E of t is greater than 0, the temperature is less than the set point, and therefore we have to increase Q. Now mathematically, these two conditions can be expressed using a relationship, using a function between the control error and the heat input to the process. There are many ways of relating the control error to the amount of heat added to the tank, but one simple idea is to choose the amount of heat added to be proportional to the control error. In other words, if the control error is large, we're going to either add large amount of heat or remove large amount of heat. The control error here in this equation is multiplied by a positive constant, and it's called proportional gain. Now it's very easy to see why such an equation would work, because if Kc is positive and Et is less than 0, according to condition 1, Q prime must be less than 0. In other words, we have to decrease Q. If Kc is negative, E of t and E of t is greater than 0, then Q prime t is going to be positive because we have to increase the amount of heat added to the process. So it makes perfect sense. We have simply translated the two qualitative requirements for keeping a process at its set point into a simple proportional or linear equation between the control error and the heat input. And now this equation is what we call a controller. A controller is nothing but a set of rules or a set of equations, an algorithm that decides how to change the control input, which in this case is the heat input, to the process. We are arguing through this idea that the heat input to the process must be changed in such a fashion that it is proportional to the control error. So this equation is what defines our controller. A controller is just like a model in that it is defined by a set of ODEs and algebraic equations. In this case, the controller is defined by a single algebraic equation. We're going to look at other types of controllers where the controllers are going to be defined by either differential equations or integral equations. Now what I would like to do is we have derived an equation, an expression for a control algorithm. We can put everything we know so far, everything we have done so far together and create what is called a closed loop system. The process we have already derived a transfer function for the process. T over Q is going to be equal to some transfer function g of s. The output of the process is T prime, the temperature, which is subtracted from the set point to derive the control error E of s, which is then passed on to the controller, where the controller algorithm is simply Q equal to Kc times E, which then outputs the heat, the amount of heat that needs to be added or removed from the process to the process. Now the process itself without the controller is what is called an open loop system. But when you put the process in series with the controller and have this feedback system where you're feeding the temperature back into the controller, you have what is called a feedback control system. It's also called a closed loop system, which is the opposite of an open loop system. An open loop system is one where you simply have a process but there's no controller. A closed loop system is one where you not only have the process but also the controller. This type of a controller where the controller output is related to the control error by a single proportional constant is what is called a proportional controller. Just a side note here, the controller output is the process input and the controller input is the controller error. It's very easy to derive the transfer function of a proportional only controller. It is simply the constant Kc. To understand what happens to the control error, the input into the process, when there is a step change in the set point, let us assume that the set point changes from an initial value of t1 to a final value of t2. The corresponding Laplace transform of the change in set point is t2 minus t1 over s. And ideally, if we have a good controller, we would like the temperature to follow the set point and reach the new set point as t goes to infinity. In other words, E of t must go to 0. With an ideal controller, it is perhaps possible to ensure that the control variable tracks the set point exactly with no error between. However, implementing this ideal controller is often extremely difficult and in many cases impossible because real processes do not have enough input power to push the process variable exactly to the set point in infinitesimally small amount of time. On the other hand, typical processes exhibit a response where the process variable, the controlled variable, eventually reaches the set point, but with a certain amount of error, as shown in the graph here. Now we can use Laplace transforms and derive an expression for the Laplace transform of the control error. We know the Laplace transform of the set point, and therefore we substitute that here. And when it comes to the temperature itself, we have a transfer function typically for the process. We multiply that transfer function with the input to the process, which in our case, in the case of the heating tank example, is Q prime. And Gs is the transfer function of the heating tank. Now that we have a controller, we can replace Q with Kc times E, which is the proportional controller. Rearranging the terms in this expression, E of s is going to be a Laplace transform that is shown here. If proportional controller were to leave no error eventually as t goes to infinity, we should be able to find that using the final value theorem. So limit of E of t as t goes to infinity is equal to limit of s going to 0 of s times E of s. You will notice that this limit in fact does not go to 0 as s goes to 0. G of 0 must exist for this limit to exist. In other words, if I were to plot the response of a proportional controller to a step change, we will notice that the response will never reach the set point. The actual temperature will never reach the set point. And there is always going to be an offset whose value is 1 over 1 plus Kc times G0. No matter what or how the response looks, the eventual offset is typically going to be the same. However, as I mentioned in the previous lecture, it is possible to arbitrarily increase Kc or make it so large that the difference between the set point and the actual response is going to be negligible. But that response is impractical because it requires, in the case of the heating tank example, large volumes of heat to be supplied to the process. That is often physically not possible. Notice that G of 0 is the gain of the transfer function. This is something that you may want to prove. Show that by simply substituting s equal to 0 in a stable transfer function, we get the gain of that transfer function. So to summarize, P controllers often lead to a non-zero offset in the control error. However, it's theoretically possible to reduce the offset by as much amount as you want, but that solution is often practically not feasible. So it turns out that using what is called integral action allows us to remove the offset that arises due to a proportional only controller. So let's start with the integral controller. The basic idea is very simple. In a proportional controller, we are using the current value of the control error to determine how to change the input to the process. Whereas in an integral controller, we look at the past of the control errors from current time all the way to time 0 when the experiment was started. We use that integral to determine the current amount of input that we are going to apply to the process. And that integral is multiplied by a constant 1 over tau I, where tau I is the integration time constant. It's a constant whose value is chosen by the user. Integral action, unlike proportional action, helps in removing the offset between the set point and the control variable. And this is possible intuitively because the control output or the process input keeps changing until the control error goes to 0. If we were to plot time versus the control error, we will notice that the area under this graph is used as an input to the process by the integral controller. However, the disadvantage with an integral controller is that it is very sluggish. No or very little control action takes place until the error has accumulated over a period of time. In contrast, proportional controllers take immediate action. They are extremely fast, and therefore it is common practice in the industry to use some combination of proportional and integral actions instead of using either proportional or integral actions separately. To understand how proportional and integral actions work, let us consider a step change in the set point. The step change in the set point is shown in the left-hand plot. As soon as there is a step change in the set point, we will notice an immediate change in the control error as well, because the control error is directly proportional to the set point. And in fact, when the closed loop system is broken, in other words, when there is no feedback, a step change in the set point will instantaneously lead to a step change in the control error. When there is a step change in the control error, the proportional and integral controllers behave differently. They respond differently. With a proportional only controller, the step change in the control error leads to a spike in the input at the instant when the step change occurs. And this spike is going to be proportional to the control error. And the proportional constant is Kc, the controller gain. The spike is also sometimes referred to as proportional kick. On the other hand, if an integral controller is used, there will be no instantaneous increase in the heat input to the process. Instead, because of the integral action, we will notice a steadily increasing input. Clearly, the proportional controller takes rapid, quick action on the process, whereas the integral controller takes slow action but will eventually lead to an offset-free response. And therefore, let's try to put together the proportional and integral controllers in this fashion. There are many different ways in which one can combine the proportional action with the integral action. However, what I'm showing you here is the most common way of integrating or putting together the proportional and integral actions. This is also referred to as the series form of a PI controller. Now, the corresponding transfer function of a PI controller can very easily be obtained by simply applying Laplace transforms on the expression for the controller. That leads to a first-order transfer function of the form shown here, Kc times 1 plus 1 over tau I s. This is one of those transfer functions that you must take away from this course and remember very well as a process engineer. Let's try to find the step response of a PI controller and understand how a PI controller works. Assume that the control error, the transfer function or the Laplace transform of the control error is 1 over s for a unit step change in the set point. The controller output, therefore, is going to be, in time domain, a combination of a step and a ramp, where the first term is due to the proportional action and the second term is due to the integral action. Intuitively, the response of a PI controller must be the combination of responses of the proportional and integral controllers, which is exactly what we see here. The proportional action results in a quick, immediate action right at time 0, and the integral action takes over after that, adjusting the input to the process in such a way that it eventually pushes the process to the set point. Now, proportional action in some way represents the present because it's proportional to the current control error. The integral action is proportional to the past of the control error, therefore it represents the past. But it turns out that one can also use the future of the control error to determine how the input to your process is going to be changed. Now that process or the controller that allows you to look at the future of the control error is what is called a derivative controller. And the idea behind derivative controller is quite simple. We look at the derivative of the control error and determine if it's increasing or if it's decreasing. If it's increasing, we take the appropriate action of reducing the heat input to the process. If it's decreasing, we take the action of increasing the heat input to the process. So that is the derivative controller, and it can be incorporated in a controller by simply using the following expression in time domain. The derivative action is proportional to the derivative of the control error, and the proportionality constant is what is called derivative time constant. The derivative of the control error provides information about the future of the control error. So let's start with the derivative controller. Just like the proportional and integral controllers, the derivative controller is a function of the control error. And in fact, a derivative controller, the control action from a derivative controller is obtained by differentiating the control error with respect to time and multiplying it with a derivative time constant, tau d. The idea behind derivative controller is to be able to look ahead in time in terms of how the control error is going to change in future and use that information to take appropriate action. So for instance, if you were to plot the control error versus time, as shown here on the right hand side, at a given time t0, the derivative at the profile representing the control error is dE over dt. We can certainly use that information to determine if the control error is increasing or decreasing and take appropriate action. The tau d is the derivative time constant, and dE over dt provides information about future values of E of t, the control error. An interesting observation with respect to the derivative controller is that when the control error is constant, it takes no action. In other words, when E of t is a constant, the derivative is going to be 0, and therefore the output of a derivative controller is 0. In other words, if the control error is constant, derivative controller will take no action, and therefore it will not be able to remove offsets between the set point and the control variable, unlike the integral controller. Now, given the differential equation that represents the derivative controller, we can derive a corresponding transfer function. So for instance, we can put together the proportional and derivative actions and create a PD controller as follows. Applying Laplace transforms, we can derive a transfer function for a PD controller, which turns out to be Kc times 1 plus tau ds. It turns out that this transfer function of a PD controller has a numerator order that is greater than the denominator, which means, as we have learned a few times in the past, this is a transfer function that cannot be realized in practice because the numerator order is greater than the denominator order. And the reason for that is if you were to approximate the derivative at t0, you will have to use values of control error at t1 and t2. t1 is in the past and therefore you know that. t2 is in the future and therefore you don't know that. As a result, finding the derivative is not easy, and you have to use certain types of approximations of the derivative in order to implement the PD controller. Now let's put together the proportional, integral, and derivative actions to create what is called a PID controller. PID controllers are perhaps the most widely used basic controllers in the process industry. In fact, hundreds of thousands of these controllers are used in a variety of industries such as oil and gas, pulp and paper, biotechnology, or pharmaceutical industries. It is very natural that we put these three actions, P, I, and D, together to create PID controller because proportional and derivative actions, while they're good, they improve the speed of the response, they do not guarantee offset-free response. On the other hand, integral action guarantees offset-free response, and therefore we would want to put these three types of actions together and create a PID controller. Proportional action represents the current control action, integral action represents the past control action, and the derivative action represents the future control action or control error. Now we can similarly derive a transfer function for the PID controller. Now this transfer function is one of those things that I want you to remember for good from this course. The transfer function of a PID controller is Kc times 1 plus 1 over tau is plus tau ds. The tau ds, which is a polynomial fraction with a numerator order greater than the denominator order, is something that is often approximated with a first order transfer function of the form tau ds over tau cs plus 1, where tau c in the denominator is chosen to be a value that is much smaller than the derivative action. In so doing, you can approximate tau ds reasonably well. And the transfer function 1 over tau cs plus 1 is what is called a derivative filter. We can represent the PID controller using a block diagram where the input is the control error and the output is the process input by placing the proportional, integral, and derivative action in parallel, and that is why this particular form of a PID controller is also called parallel form of PID controller. If you were to read the textbook, you'll notice that there are other forms of PID controllers, including the series form of PID controller. If you're designing a controller for an industrial processor with an industrial controller, you want to make sure that you know what type of a controller is programmed in the microprocessor before you start tuning it. So the typical response of a feedback loop, closed loop response of a feedback loop, is as follows. If there is no controller, you will notice that the process output veers off the set point. If there is proportional only controller, you will be able to bring the process output closer to the set point, but you will not be able to eliminate the offset. If you have a PI controller, there will be no offset, but you will likely see oscillations, or the response is going to be slower. On the other hand, once you add a PID controller, you can improve the speed of the response and also often eliminate some oscillations in the response.